Okay, morning. We're just going to have a quick look today at the first chapter in the Further Pure book. Chapter 3 is going to be the first chapter which I'm going to cover, which is all about series. Now, we've seen series a little bit already in the Ordinary Pure side, where we looked at the sums for arithmetic and geometric series, sums to infinity, and we also introduced sigma notation. So we're going to be following on, particularly with the sigma notation, which we know is a really clean way of writing some of our summation sums. When we begin to look at this. Now, the chapter is actually quite short. There is actually quite limited content in this chapter because what we're going to look at basically is 4 different summation sums which we need to be aware of and which we need to know how to deal with. Later on, actually, in the Further Pure book, you are going to learn to prove these by induction, but for now, we're just going to take these as read and use them as we see fit, really. Okay, so I'm just going to take you through these different formulas which we need to look at a few different quick examples, and then hopefully you should be able to have a good go at some of the questions on this topic. So just going to flip the camera around and we're going to have a quick look. So the first part of chapter 3 looks at 2 formulas. Now, we should be familiar with this sort of setup here, the sum of, these terms up to n. We should sort of recognise what that sort of means. Just quickly, these first 2 formulas are not given, okay? So we're going to have to learn both of these. Now, for the first one, this is for the series of constant terms, as in the sum, isn't it? This one here, we should know it's going up by, it's just the sums of 1 n times, so 1 plus 1 plus 1 plus 1. So whatever value of n we had, for example, if we had 20, we'd expect the sum to be that number, wouldn't we? Okay, so a really nice straightforward one to learn to kick off with. The sum of our constant terms up to n will just be n, okay? So that's a nice easy one. Interestingly, it's linear, n. Our second one, this is for the sum of the first n natural numbers. Reminder that n natural numbers, what we're talking about there is the positive integers. That's important when we're considering our series, just the positive integers. But if we consider here 1 plus 2 plus 3 plus 4 all the way up to n, that's essentially the sum which we're doing here. We can surmise that as a sum as half n multiplied by n plus 1. Okay, so there's our first 2 formulas. Those are what you're going to need for exercise 3a. Moving a little bit further through the chapter, we come on to look at the sums for our quadratic and cubic, some of the squares of the first n natural numbers, and some of the cubes of the first n natural numbers. Now, these are given, these ones, these slightly more complex ones, but I think there's something which we should really try and recognise here. The expression up here was linear. This one here is quadratic, n times n. The sum of our square numbers is going to be cubic, and the sum of our cube numbers is going to be, quartic, okay? So we can see a little bit of a pattern there emerging, but we're going to need to be able to use these formulas as they are written just here, okay? And they should be pretty straightforward. It is a matter of substitution, which we should be pretty comfortable with. Now, in terms of using these, there's a few little tricks which we need to be aware of, which I think we'll just talk through. The first and most important trick which we need to be aware of is we want to be a little bit careful when we have any sums. You'll notice I've not actually put the function in here. It doesn't matter which function it is. When our bottom number is not r equals 1, okay? When we're not starting at 1. That's something which we need to be a little bit careful with. And the way in which we're going to deal with this is we are actually going to go all of the numbers summed up to n from the start, subtract the numbers before r equals k. And if we're considering numbers before r equals k, we should appreciate why we have to use k minus 1, 1 to k minus 1 as the ones which we want to lose from our summation. Okay, so that's our first trick. If we ever have a question where we don't have r equals 1, we need to put into practice this approach here in order to make our lives a little bit easier. Second thing which we need to be aware of is if we had the sum of a function with a coefficient, we can actually take the coefficient in front of our summation sign, okay? What I mean by that is, let's just imagine we had, you know, some of our first n natural numbers multiplied by 3, is we can actually take the 3 in front. Just purely use the summation formula for our r and then multiply our results by 3. And similarly to this, we can also split different summation functions up into individual terms. So that's how we're going to sort of start this chapter. We're going to look at a couple of examples now just to sort of put those tricks into practice. The actual formulas themselves, we just need to get a bit of practice and we should be fine with. So to start off with, here's this example which I'm talking of when we don't have r equals 1 at the bottom. We want the sum of the first natural numbers here between 50 and 21. So what we're going to do is the sum of the first 50 natural numbers subtract the sum of the first 20 natural numbers, okay? And because this is sigma r, we're going to use our sigma r formula, which was half n plus 1. So you can see me here doing half 50, 51, and half 20, 21. And really nice, straightforward. When it's numeric, obviously we're expecting a numerical answer, which should be really straightforward. Moving on slightly, and this one is an example which will help you with exercise 3b. We're looking here for the sum of this thing here. Now, because this is being factorised, we want to expand all of our brackets and actually see what we're actually trying to find the sum of. We're trying to find the sum of 2r cubed plus 5r squared minus 3r. Now, this is the bit which I was talking about where we can split our summation up and we can take the coefficients outside. We're going to want, okay, 2 lots of the sum of the cubed natural numbers, plus 5 lots of the sum of the squares of our natural numbers, subtract 3 lots of the natural numbers. Okay, so we can actually split this up into 3 discrete stages and then multiply it out by the coefficients at the end. And I'm not going to finish this question, but what we would do is obviously substitute n into our r cubed formula, n into our r squared formula, and n into our r, and then multiply them by 2, 5, and minus 3 respectively before simplifying our answer, okay? And it's actually quite likely, this is an algebraic question in contrast to this numeric question, that this will be probably a show that question where we're actually looking for a given result. And it's also quite likely that we'll have to factorise our expression once we have got our answer. Final thing which I just wanted to mention in this video before we get started on some work is the word hence. Now, it might well be that we've got a question where we've worked out the sum of our given question up to 4n minus 1, i.e. algebraically, and again it's likely to be a show that question. It might then say, hence find this sum, 1 to 99, for the same summation. Now, obviously, the inference here is that we should be able to do something clever with our answer from part A to get an easy answer to part B. And the idea here is that if we wanted to do r to 1 to 4n minus 1 and r to 1 to 99, we can actually equate our upper boundaries there, and we can just substitute n is 25 into our answer to part A to get our answer for part B. Okay, so that is the introduction which we need to have a little look at for series. It's not, I don't think, a particularly challenging chapter for the further pure level, which we're going to be looking at shortly. A few things to remember: 4 key formulas, some of which are given, some of which aren't given, and then those 3 key tricks which we need to be aware of. Making sure that we use r equals 1, and if it's not r equals 1, then we need to do some sort of adjustment around that. Splitting up our actual summation and taking the coefficient out front. And if we remember that, we should be absolutely fine with this topic. Okay, so that's the video introducing series. Thanks for watching.